Hey everyone, welcome. Today we're working on the trees questions from the LeetCode roadmap. So trees are graphical data structures that are composed of nodes, and each node has one parent but can have multiple or zero children. So there's a special case here where lots of questions are asking for binary trees. That's a special case where the trees have at most 2 children. So every node in a tree has children, and the children are the roots of their subtrees. So that leads to a lot of recursive algorithms when working on tree problems. So without further ado, let's get started on the first question, invert binary tree. So given the root of a binary tree, we want to invert the tree and return its root. So by invert, the question means we want to swap the left children and the right children. So the 2 and 7 are swapped here, but also within the left child and the right child. The 7's elements, 6 and 9, are swapped to be 9 and 6. And within the left child, the 1 and 3 are swapped to be the 3 and 1. So we can quickly see that we want to recursively swap every child. So we want to recursively swap the left child, swap the 7, and swap the 2, and then swap the left child to be the right child and have the right child be the left child. So let's start coding this question. First, we should check if root is none. So if root is null or none in Python, we should just return nothing, because we're not really inverting anything when the root is nothing. So let's create a left branch. So we're recursively traversing and inverting the left branch. So left branch should be self.invert tree. We can just call this main function here because we also want to invert the left branch. So root.left, and let's do the same thing for the right branch. So right branch, self.invert tree, root.right. So after we've recursively inverted the left branch and the right branch, we need to assign the left branch to the right. So root.right equals to left branch, and root.left equals to the previous right branch. So after that is reassigned, we can return the root. So let's try running that. Nice, okay, that worked. So let's try submitting it. Nice, okay, that worked. So moving on to the next question, maximum depth of a binary tree. So given the root of a binary tree, we want to return the maximum depth. So the tree's maximum depth is the number of nodes along the longest path from the root node down to the furthest leaf node. So in example 1 here, the output is 3 because we can travel from 3 to 20 to 7. So that's 3 nodes on the path, so we get an answer of 3. So in case 2 here, there's no diagram, so let's use this. There's 2 nodes on the path from the root to the furthest leaf node, so we're going to return 2. So in this question, we need to check basically how many layers there are in the tree. So we should travel down layer by layer, but we can also use a recursive approach. So we see how many layers are in the next, how deep the next node is, and then add 1 to it. But there's also 2 options. We can traverse the left one and the right one. So we should take the longest of the depths from the left and the right and add 1 to it to include the root node. So let's start coding it. First, we should always check if root equals to null, in which case return 0 because there's 0 path on the longest. There's 0 nodes in the longest path. So left depth, this is going to be self.max depth. So we're calling this on the left side, root.left. Otherwise, we're calling it on the right side, right depth equals self.max depth, root.right. So after that, we're not sure whether the left side or the right side has the longer depth. So we're going to return 1 plus the maximum of the left depth or the right depth. So let's try running it. Cool, okay, that worked. So we're doing this 1 to include the root node inside of this path here. So because we want the maximum of the left and the right, but also adding 1 to include the root node here. So moving on to the next question, diameter of a binary tree. So given the root of a binary tree, we want to return the length of the diameter of the tree. So the diameter is the length of the longest path between any two nodes. So in the previous question, we're talking about the longest path from the root to any node. Now we're talking about the longest path between any two nodes. So this path may or may not pass through the root. So the length of a path between two nodes is represented by the number of edges between them. So here in this question, the longest path is 3 because we can go from 4 to 2, 2 to 1, and 1 to 3. So that's a distance of 3. So in this case, we're actually going through the root node, but we also don't have to go through the root node. So at the root, we want to consider the depth, the maximum depth of the left side, the maximum depth of the right side. So the maximum diameter is either the left plus the right, or it could be the maximum diameter of a subtree, because it's possible that the subtree has a longer diameter that doesn't pass through the root node at all. So at every step, at every node basically, we need to see the maximum depth of the left side, the right side, and also calculate the maximum diameter if we're using this node. So we need to have a recursive function because we need to get not only the maximum depth, but also the maximum diameter. So let's call this get height and diameter, and it takes a node as an argument. So if node equals to none, the maximum depth is going to be 0, and the maximum diameter is also going to be 0, so return 0, 0. So otherwise, we can call this function recursively to get the maximum left height, and the left diameter. Get height and diameter. So we can do the same thing for the right side. So right height, right diameter equals to get height and diameter node dot right. So we have the maximum height from the left side and the maximum height from the right side. So the maximum height in general is just like the previous question, max height equals 1 plus max left height and right height. And the maximum diameter is either, so we're taking the maximum of the left diameter, which is getting height and diameter from the left side. So basically the left node's highest diameter, the right node's highest diameter, or we're using this node, the current node, and combining the left height and the right height. So we're saying the diameter is traveling throughout the current node. So in the other case, it's going to be left height plus right height. So after that, we're going to return a tuple. The first element is the max height, because we're returning the height first. And the second element in the tuple is the max diameter. So after we have this recursive function, we can just call this on the root. So get height and diameter. We don't need the element at 0 because that's the height. We need the element at 1 because that's the diameter. So let's try running that. Cool, okay, that worked. So this question is a little bit more difficult because we not only need the height, but also the diameter, and we need to calculate the maximum diameter at each node. So to calculate that, we need the left plus the right heights to see what the maximum diameter is if the diameter passes through the current node. So if it doesn't, we're returning the maximum of its left child's diameter and the maximum of the right child's diameter. So moving on to the next question, balanced binary tree. So given a binary tree, determine if it's height balanced. So what height balance means is that the depth of two subtrees never differs by more than 1. So in example 1 here, the left subtree 9 has a depth of 1. The right subtree 20, 15, 7 has a depth of 2 because we're going down 2. So this does not differ by more than 1. And in the subtree 20 here, 15 and 7 have the same depth. So this example 1 here is a height balanced binary tree. So in example 2 here, we can see that the left child of 1, so this tree here has a depth of 1, 2, 3, while the right child has a depth of 1. So 3 and 1 has a difference of more than 1. So this example 2 here is not height balanced. So we're trying to determine whether or not our binary tree is height balanced. So to determine if it's height balanced, we need to check the heights of the left child and the right child, and we also need to check if the left child is height balanced and also the right child is height balanced. So just like the previous question, we need two things. So let's create a recursive function to return those two things. Let's call that get height and balance. And that takes in the node as a parameter. So if node equals to none, so if we have a null input, the height is going to be 0, and a null input is actually height balanced. So we're returning true here. So we can get the left height, left balanced. This is very similar to the previous question's code structure. We're just calling this recursive function that gets two attributes from the tree. So we only have to recurse it once. Balance node.left and right height, right balance equals to get height and balance. I missed and here. On node.right. So max height, just like before, is going to be 1 plus the maximum of the left height and the right height. And to check if it's balanced here, is balanced. So we need the left side to be balanced, so left balanced. And the right side to be balanced, so and right balanced. And also the left side's height and the right side's height should not differ by more than 1. So we can do abs, left height minus right height is less than 2. So this makes sure the left subtree is balanced, the right subtree is balanced, and also the heights of the two subtrees never differs by more than 1. So after that, we can return max height and is balanced. So after that, we can do return, we can call this recursive function get height and balance. In our question, we don't care about the height. All we care about is if it's balanced or not. So we'll call it at root and call the element at index 1, which is balance. Nice, so that works. Try submitting it. Cool. So this is a very similar question to the previous question, where except we don't care about the diameter anymore, we care about whether or not it's balanced. But to find the diameter and to find whether or not it's balanced, we always need height. So we have this get height and balance recursive function. So moving on to the next question, same tree. So given the roots of two binary trees P and Q, write a function to check if they're the same tree or not. So two binary trees are considered the same if they're structurally identical and the nodes have the same value. So in example 1 here, these two trees have exactly the same structure. They have root at 1, left is 2, and right is 3. And also their values are identical. So example 2, the nodes have the same values, but the structure is different because 2 on the left side is the left child, on the right side it's the right child. So they're not the same tree. In example 3, the orders of the children are swapped, so 2 instead of being the left child, it's the right child. So again, that's false. These trees are not the same tree. So how do we code this? We need to recursively check that the value we're currently at is the same in P and Q, and also the left child is the same and the right child is the same. So first let's do a null check. So if P equals to none and Q equals to none, we want to return true because two null pointers are actually the same tree. So however, if P equals to none or Q equals to none, return false. So what this line is checking is if one of P and Q is false, because we know that if P and Q are both none, we would have returned true already. So this line, this if statement only returns true if one of P is true and Q is false, or Q is true and P is false. So if only one of P or Q is none, then we're going to return false because that means we don't have the same structure. So now let's call this function isSameTrue recursively on the left and the right children. So we can create a boolean is left same. This is going to be self.isSameTree p.left and q.left. So is right same because we need the left child and the right child to be the same. So self.isSameTree p.right q.right. So after that, we can just return p.val. We need to make sure the values are exactly the same. So p.val equals to q.val. This is never going to null pointer exception because we checked that p and q aren't none. So return p.val equals to q.val. So making sure that the values are the same. And we also need to make sure the left subtree is the same. So is left same. And the right subtree is the same. So is right same. So let's try running that. Cool, okay, that worked. Let's try submitting it. Nice. So moving on to the next question. So subtree of another tree. Given the roots of two binary trees, root and subroot, we want to return true if there's a subtree of root with the same structure and node values of subroot, and false otherwise. So basically we're doing this previous question, same tree, except we don't only want to check the root is the same, we also want to check each of the children is the same. So we can recursively check is same on root with subroot. So let's copy over the code in the previous question real quick. So def same root subroot. I think it was P and Q, so P, Q. So with this function here, we can use that to help us do our current question. So at every node in root, we want to check if it's the same. So here we want to check if root or is same root subroot. So if it's the same, we're going to return true immediately because we found an identical subtree. So we also want to do a none check here. So if root equals to none, we want to return false. So now that we know root is not none, so root can have children, and also root is not the same as the subroot, we're going to check the left child to see if it's the same as the subroot, and we're going to check the right child to see if it's the same as the subroot. So all we have to do is return self.isSubtree. So we want to check the left child first, so root.left and subroot. And also let's check the right child. So or self.isSubtree root.right subroot. Because either the left child or the right child could be the same as the subroot. So let's try running that. We renamed the function here, yeah. Don't need same anymore. I think that should work. Nice. So this question just takes the idea from the previous question, except we have to check if the current root is the same as subroot, but also the left and right child of the current root if root is not none. So a very similar idea, just using the function we did in the previous question. So moving on to the next question. Lowest common ancestor of a binary search tree. So given a binary search tree BST, find the lowest common ancestor of nodes of two given nodes in the BST. So the lowest common ancestor is defined between two nodes P and Q as the lowest node T that has both P and Q as descendants, where we allow a node to be a descendant of itself. So in the first question, our P and Q are 2 and 8. So the lowest common ancestor of both 2 and 8 is the 6 here. So in the next question, we have P and Q being 2 and 4. The lowest common ancestor is 2 because the question said a node can be an ancestor of itself. So that makes sense. In a binary search tree, remember, the left child and every children of the left child is smaller than root, and the right child and every child of the right child is going to be greater than root. So we know that if P and Q are like 2 and 8, then the lowest common ancestor has to be between 2 and 8 inclusive. So right off the bat, if P and Q are 2 and 8, the numbers for the lowest common ancestor can only be 2, 3, 4, 5, 6, 7, 8. So we can do this check here. If P dot val is less than equal to root dot val is less than equal to Q dot val, or remember, P doesn't have to be less than Q. So it could be that in example 3 here, P is greater than Q. So, or if P dot val is greater than equal to root dot val and is greater than or equal to Q dot val. So if either of these cases are true, we're going to return root. So root is the lowest common ancestor of both P and Q. So otherwise, if P dot val, so now we have to decide whether we want to search the left subtree or the right subtree of root. So suppose P and Q are both smaller than root's value. So P dot val is less than root dot val, and Q dot val is less than root dot val. So if they're both smaller, we want to be searching the left subtree because the left one is a smaller subtree in a binary search tree. So we're going to search the left one, so return lowest common ancestor. To do self here. Ancestor with root dot left, P and Q. So otherwise, we want to search the right subtree. So we could just do an else here, or we could just type it out. P dot val is greater than root dot val, and Q dot val is greater than root dot val. So in this case, we want to return self dot lowest common ancestor root dot right, PQ. So let's try running that. Cool, okay, that worked. Nice. So this question, basically, the main idea is just checking if the current root is the lowest common ancestor, in that the current root is in the range between P and Q. So if it isn't, we need to decide whether we checked the left subtree of the current root or the right subtree of the current root. And that gets us our answer. So moving on to the next question. Binary tree level order traversal. So this is a super classic question where we're given the root of a binary tree and we want to return the level order traversal of its nodes. So level order traversal means we return all the nodes in the first level from left to right, so 3 in this case. The second level from left to right, so 9 and then 20, and all the nodes in the third level, so 15 and 7. So this is a classic use of a breadth first search, where we want to search the tree level by level. So breadth first search takes advantage of a queue because we can take the current node and then input its children in the queue, so we're going to search those next. And then we're going to search the children of the children next into the queue. So we always do the nodes closest to the top first and always left to right first. So first let's do a none check. If root equals to none, return nothing, because there's nothing in this entire tree. So let's create a BFS. This is a DQ. And in the DQ, we want to put our root. So the syntax is basically creating a list with the root and then using that list as the creation parameter for a DQ. So the DQ has a single element that is the root inside it right now. So let's also create our answer as an empty array. So while len BFS, so while there's still roots that we haven't breadth first searched yet, so while len BFS is greater than 0, we want to pop out every element in the current level and then put that in answer. So how many nodes are there in the current level? Well, it depends on the size of BFS. So size equals to len BFS. And now we want to get all the elements inside the current row. So for I in range size, that means we're going to pop out nodes from the DQ size times. So node equals to bfs.pop left, so this pops it from the left side, which is the first element in the queue. So row.append, we want to add this element's value, so node.val, to our row. So after that, we want to add the children of our current node. So, but only want to add them if they're not null. And we want to add the left one first, then the right one, because we're going left to right. So if node.left is not equal to none, so it's not null, we want to push it. So bfs.append node.left, and let's do the same thing for the right here. So node.right is not equal to none, bfs.append node.right. So after that, we're done with the current row, and we should put it to our answer. So ans.append our current row. After that, this while loop is going to BFS the entire binary tree, so we can just return answer after that. Let's try running it. Nice, that worked. So let's try submitting it. Cool. So this question is very classic. We're taking advantage of BFS because it searches the entire tree level by level, just like the question wants, because we want a level order traversal. So we're taking the first level, the second level, the third level, and so on. So moving on to the next question, binary tree right side view. So given the root of a binary tree, imagine yourself standing on the right side of it. So return the values of the nodes that you can see ordered from top to bottom. So again, it's a level order, as in we're returning our answer from top to bottom of the binary tree, but we only want to return the rightmost element of every single level. So we can do a very similar approach to the previous question, except instead of returning the entire row, all we have to return is the rightmost element. So let's just write the same structure as the previous question, starting with a none check. If root not equals to none, we just return nothing. Create our answer and create our DQ. This should have root in it. So while len BFS, while there's still elements to breadth first search, we're going to get the size. So this is how many nodes there are inside a level, so size len BFS. And we also want the last element of every single row. So let's create a last element, just initialize it to -1 for now. So for I in range size, node equals to bfs.pop left, last equals to node dot value. We're setting the value of last to the current nodes. Because we're going from left to right, last gets replaced as we're traveling from left to right. So eventually, last is going to take the value of the last or the rightmost node inside a single level. So after that's done, we're going to populate the next row. So if node.left is not equal to none, this is just like the previous question. So we want to push it, so bfs.append node.left. If node.right is not equal to none, bfs.append node.right. And after we're done with a row, all we have to do is put the value of the last element into our answer. So ans.append last. And after that, we can just return answer. So return ans. Let's try submitting it. Nice, that worked. So there's quite a lot of questions in the tree section, so we're going to split this off into 2 videos. That's it for this video. Thank you guys for watching, and I'll see you in the next video.